fuse around at will, you also get exactly the same regulation to differences in size in multicellular gradients as well, where you have lots of different cells communicating with each other. So in some ways, I just wanted to put this in. I'm not saying that it's another toy model, but you have the same problem, that these embryos are actually having to set up their own spatial system as they develop. And they have to do so in a way that responds to how many cells they've got. They do it adaptively. And you get extreme cases of this in identical twinning and things like that. That you have pattern, essentially spatial structure being established on a ball of cells into a developing embryo. The whole thing can split into two and very quickly rearrange so that it re-establishes a spatial order within it. So in terms of the more general question of what are the mechanisms underlying generation of order, I think that biology gives us actually some really interesting cases to look in, and what's nice is that we're now starting to uncover the mechanisms for this kind of regulative establishment of spatial order within the embryo. And it's all to do with nonlinear interactions between the parts. But in a nice way, that all of those interactions are indeed local. That all well, as far as we know, unless there's some morphogenetic, what does Shelley thingy call it? Morphic resonance or something, or I don't know, these bizarre ideas. You don't have to go to these bizarre ideas. What you actually have is that cells are only interacting locally with each other, but in those simple interaction rules, you actually encode information about the whole system. So you encode non-local information in local interactions in a very boring and trivial way in some ways from the standpoint of physics and chemistry, but you do really quite exceptional things with it at the level of the embryo.
So what is the boring way?
What is a boring way? Well, cells just communicate their state to each other in a fairly rough way by signaling between proteins, basically. There's no magical non-locality in here. There's a very dull non-locality. So there's non-locality. There is effective non-locality based on local interactions.
Emergent non-locality.
Emergent non-locality. I don't like emergent, that word, but essentially yes.
What about long-range order? Cooperative phenomena.
Yeah, cooperative phenomena, exactly. But what they do is give you this very nice. It has this nice parallel with what we're trying to do with process and getting space-time out of process. Is that here you've got simple interactions between things actually giving you a space-time that's, well, I haven't mentioned time, but I also work on how embryos set time as well by oscillations, by internal oscillations. And they do that in exactly the same way, so segmenting your own body. So we have the segmented bodies too. Insects are much more obvious, but we do too. And that's actually done by an oscillator turning a spatial oscillation into a spatial periodic pattern. And it does so you always get exactly the right number of segments, however many cells you've got. And so again, it's doing this, it does a beautiful, the interactions in biology are set up in just a way that you get exactly the right space-time out that you need for what you've got, which I think is really nice. But it's nothing to do with physics.
It's very suggestive. And when you've got these internal oscillations crop up a bit, not only in embryology, but in the study of physiology.
Yeah, absolutely. Yeah, they're pretty much ubiquitous. But they're
related obviously to internal time clocks and things like that.
Yeah.
There's an extremely interesting essay, you probably know it, by it's published a couple of years ago, but Bailey, Longo and Bailey, do you know it? I translated it.
Right.
Yeah, it's okay, you know that. It's which is about precisely this.
Yeah, so embryos
long-range order and
embryos are doing really nice things in setting up space and time for themselves.
I don't know anything about this at all, Nick, but can you just confirm what seems implicit in what you're saying, that the cells remain in fixed positions? There's no migration of cells throughout the organism?
In multicellular systems, you get migration, you get cells dying if they're in the wrong position, you get all sorts of things happening at the next level.
Right, but it's not connected. It's not.
But in this case, so specifically in this case, you haven't even got cells. All you've got are nuclei, and no, they don't move relative to each other.
Right.
So in the picture I showed on the first slide, each dot was a nucleus, but there are no cell membranes, but they're fixed in their positions in there. And
Right.
occasionally they will divide and give you 2, but well, they do it synchronously, in fact.
So you haven't got marshals striding around
No.
putting everything in order.
No, absolutely not. So there's no long-range movement. And that nice stripy pattern, if you actually model the network, you don't even need any diffusion between the... So there are things interacting between the nuclei as well as this global gradient, but you don't even need any diffusion of them. So it's weird. I mean, we don't have a full picture of how it works yet. But,
That isn't, sorry, just to, I mean, you mentioned the word